Okay, we'll start this again. And we just had Robert join us, so thanks for showing up. We just had some audio issues, so we're back online here. So modules 1, 2, and 3 we're going to discuss tonight, the pertinent points, and if we have enough time, we're going to get into the operation of a TXV, but I want to make sure that everyone understands sensible and latent heat refrigeration cycle, what happens when we have an overcharged and an undercharged system. So we'll pop back over here to our heat and temperature graph from our textbook. And what we're going to look at, we're going to back up here. Got a screen share with you first. Okay, now we're on our heat and temperature graph, and we're going to relate this not to water, but to our refrigerant later on when we do the refrigeration cycle. The graph goes from point 1 to point 5 to illustrate freezing water to steam, but we only want to take a look at points 3, 4, and 5 because this is where the refrigeration process happens, and just a little bit above 5 as well. So the graph depicts water in this instance and just the small amount of heat it takes to raise the sensible heat of that water. And once that water starts boiling, change of state holds that water at the constant the saturation temperature, where it is both liquid and vapor, and any heat added or removed will change the state either into vapor or back to liquid. It takes a tremendous amount of energy to do that, and this is where the refrigeration process happens in the evaporator coil. And when we are looking at the evaporator coil, this is where things start to happen right here at point 4. And right just above point 5 is where it leaves the evaporator coil. So let's take a look at refrigeration circuit. So go back. We're going to start at point 4, where just below point 4, where the refrigerant coming into the circuit is liquid. And I know, Mike, you just started module 3 today, so hang in there with us. So point 3 on the graph corresponds to right here on a refrigeration cycle where we have all liquid coming into the metering device. Now when this metering device drops the pressure of the refrigerant and it begins to enter the coil, it starts to boil just like this at point 4. So all of the BTU that's in the air from the hot air going over that coil is sucked up into the refrigerant as it changes state along this line. So what happens is as that refrigerant starts to travel through the coil, it's boiling off, and it's absorbing all of the heat energy from the air that's flowing across it. And on the circuit that's working properly, just about the time you hit the end of your evaporator coil, we have now boiled off all of the refrigerant and it's starting to pick up the sensible heat. And that's what starts to happen. Here's the end of the evaporator coil right here just above point 5. So here's the liquid entering the metering device, and we boil it off. That's where all the heat is absorbed from the air flowing across the evaporator coil. And then as it starts to exit the coil, near the end of the coil and exits the coil, then it starts to pick up sensible heat. Everybody got a pretty good grasp on that right now? Give me a thumbs up or a thumbs down or a quick message. Any questions? Okay. And if your thumbs are up, then they stay up until you put them down. So I'm assuming if your thumbs up, we're good to go. Okay, let's go back. Michael, are you good? Okay. So let's go back. Start again. So change the color of our. All right. So let's go through the refrigeration process. Let's just start right here where we started on our temperature graph, and we'll go all the way through on a circuit that's working properly, refrigeration circuit that's working properly. So this is your outdoor unit, condensing unit right here. As the refrigerant leaves the condensing coil, it is a solid column of liquid, and it should be subcooled liquid so that it's not flashing over, because every time you have a joint, an improperly, or an elbow or an improperly reamed out joint, you start to have pressure drops in this line, and if you don't have subcooling, any little pressure drops, you're going to end up starting to boil off this refrigerant, and it's going to start to change state and rumble in this line before it comes through. So we want a solid column of refrigerant hitting the metering device. Once we drop that temperature or hit the metering device, we drop the pressure, and it immediately drops the temperature. And it shows right here, it looks like this is a solid column of liquid. It's not. It starts to flash right here at the metering device, and as it travels through the coil, it picks up heat, and it boils, 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 boils. The coil is designed so that the last part of the coil doesn't do much cooling, but it does start to add some superheat to the refrigerant, so that as we travel back through the refrigeration line to the section side of the compressor, we have straight vapor going back to the compressor. Now, a compressor is supposed to and is designed to compress vapor. If liquid starts to go back to the compressor, then we have issues. So again, this system is designed so that as the refrigerant leaves this evaporator coil, it is already superheated, because you may just have a 2 or 3 foot refrigeration line right out the wall to the condensing unit, and there's not enough time to pick up superheat through this refrigeration line. Proper place to measure superheat, if you're doing any troubleshooting, is at the exit point of the evaporator coil. So our superheated vapor comes back to the compressor inlet and is compressed. And you remember from Module 1, if you compress a vapor, the temperature rises in proportion to the pressure. So as the pressure increases, so does the temperature. And what happens is it raises the temperature of the refrigerant above that of the outdoor temperature, and it really doesn't matter what refrigerant it is. It usually raises it up to 100 to 110, 15 degrees so that it can reject the heat in the condensing coil. So at this point, we start to reverse the refrigeration process that happened in the evaporator coil, and we have all vapor entering the condensing unit. Then what starts to happen as it passes through the condensing unit, the outdoor air, which is cooler than the 110 degree or so vapor, the refrigerant starts to change state back to a liquid state. So all the heat that was gathered here in the evaporator coil, boiling it off, is rejected here at the condenser coil. And again, this condenser coil is designed so the last part of the condenser coil down here, we are now starting to subcool this liquid to send it back to the metering device. So that is the refrigeration process in a nutshell. So, are we all still good to go? Thumbs down if you're not. If you have a question, please put it down there in the chat box. Okay, good. We'll go back. Let's take a look at what happens. Let's take a look at what happens on an undercharged system with a fixed metering device. That's probably what you're going to run into most of the time when you're running a service call, because the systems that are 10 or 15 years old are the ones that are going to have leaks, and the ones that have a TXV are usually a little bit newer and you won't find as many leaks. So let's just look at undercharged or a system that is leaking, and we'll go through what happens with the refrigeration process. Okay, so undercharged system. Let's just start right here at the metering device, and this is going to be a fixed orifice metering device. And what happens is we have our refrigerant coming into the evaporator coil, and it starts to boil off. But what happens is, instead of being completely boiled off at this point of the coil, here, it's all boiled off right here. And so effectively, you have cut cooling down, in this instance, by half. Now what's happening, instead of changing state throughout this coil, it has stopped changing state right here and is starting to pick up superheat long before it's supposed to in the evaporator coil. So it's now picking up superheat from the air and coming back to the compressor with a ton of superheat. So if you're measuring, if you put your gauges on and that reflects the saturation temperature of the refrigerant in the evaporator coil, theoretically right here, and it's picking up superheat all the way through, or halfway through the coil, all the way down this line set, you're going to have a huge difference between the saturation temperature that you're reading here and the line set temperature that you're reading right here. So everyone kind of got a picture of that? Do I need to go over that again? Questions? Okay. Okay, so we do have vapor coming back to the compressor, but it is superheated, and it's not at the proper and designed temperature or pressure, and it still comes back here as vapor, and it gets compressed down into hot gas coming out of the compressor. What also happens here at the compressor is there's not enough refrigerant and there's not enough coolness in the refrigerant to cool off the compressor, so it's going to make the compressor start to run hot, but you may not notice that. But we still have our hot gas coming out of the compressor, and what happens here is the refrigerant runs through this condenser fairly quickly, so as it comes out of the condenser, it is still somewhat in the saturated state coming out of the condensing unit, and may not get subcooled until it gets partially down the refrigeration line set. So what you have with an undercharged system is you have high superheat here, and you have little to no subcooling down here, because this refrigerant runs through this coil, the condensing coil, much too quick. And it's also designed, the system is also designed to have this refrigerant back up just a little bit so that there's liquid refrigerant waiting to come out of this condenser coil as the metering device is feeding. So again, undercharged system with a fixed metering device has very high superheat because everything boils off in the coil and it starts to pick up superheat long before it should, and it has little to no subcooling because it zips through this coil and doesn't start to get backed up behind this metering device until it hits down a little bit further down the refrigeration lines. So fixed metering device is high superheat, little to no subcooling. So what happens if we're overcharged? The opposite things begin to happen. We have too much refrigerant in the circuit, and instead of being boiled off as it gets into towards the end of the evaporator coil, it's still in a liquid state at this point. And it may still be in a liquid state all the way back to the suction line or very close to the suction line where it enters the condensing unit. So what happens is there's not a lot of heat transferred to the refrigerant in the form of sensible heat until it gets a little bit further down this suction line, and we have very low very low superheat. So once again, we have too much refrigerant floods the coil, so it's all liquid as it goes through the coil. Instead of being boiled off at this point, it may not boil off until it gets down the refrigeration line or even all the way into the compressor itself. So you have liquid going back to the compressor, still in the saturated state. So as you measure with your gauges at which is again theoretically the center of the evaporator coil, the saturation temperature, and then you take a look at this, and if it's still in a saturated state, you look at the refrigeration lines, those temperatures are going to be very close to the same temperature. I've seen them exactly the same, and if in a grossly overcharged system, it doesn't even have to be grossly overcharged. You're going to know if it's 0 to 3 degrees of superheat, you know it's overcharged. Okay, are we good to go? Everybody good? Thumbs down if not. Questions? Hello, Josh? Okay, we'll go back. Overcharged system. Go back to the overcharged system. Okay, so we have liquid comes back to the compressor. It is now mostly vapor, but there is still liquid. The compressor can't compress liquid, so it starts to run that compressor pretty hard and starts to damage the valve plates and everything that's going on in that compressor with the liquid. And if it's doing its job, it will compress that refrigerant down, and we're going to have hot gas going into the condensing unit. Now, when these systems are designed, the coils are designed so that as a refrigerant comes down this the condensing coil, it starts to back up just a little bit right here so that it ensures it has a solid column of liquid. If it's overcharged, what happens is it begins to back up early on in the coil. So it sits here in this coil for a longer period of time, and this is probably one of the hardest things for me to grasp was why does the superheat go down and the subcooling goes up? And what it is this refrigerant gets backed up into this coil, and it sits there waiting to get fed through to the metering device and sits in that condensing coil for a longer period of time, so it begins to subcool even more. So what you have is, instead of having 10 or 12 degrees of subcooling, you may have 15 or 20 degrees of subcooling as it leaves the condensing coil. And that is why you have high subcooling. Now, when you're measuring superheat and subcooling and trying to check a refrigerant charge, you should go in and check the metering device, but to really just get a quick look, I always use subcooling, because it doesn't matter whether it's a fixed metering device or a TXV. If this system is overcharged, it's going to back up behind the metering device no matter what. So, that's a quick down and dirty check, is your subcooling always. So if you have really high subcooling, you have a pretty good indicator that it's an overcharged system. And then you go in, okay, what is it, a fixed metering device? So I'm looking for little to no subcooling. You don't even need to look at it. You don't even need to check any further to know that it's overcharged. Okay. Let me get a warm and fuzzy here. Okay, so everybody go up here to my mood and hit I'm fine, and then give me a thumbs up if everybody's good to go and you have no questions. Good, good. Josh, how about you? Right up there on my mood. Okay, let's go back. All right, so we just looked at the overcharged system with a fixed metering device, remembering that we have at the inlet of the compressor, we're going to have little to no superheat, and at the outlet of the condensing unit, we're going to have high subcooling. So subcooling is high, superheat is low. Now let's take a look at the difference between a system that has a low load, a plugged filter, a collapsed return air duct, a dirty coil. You don't even need to go look for it. You're going to know that it's an airflow issue from one of those reasons, or even a sofa pushed up against a sidewall return air. I've seen that happen quite a bit as well. So let's start here again from the refrigeration cycle. We have our properly charged system. So we have subcooled liquid, properly subcooled, coming out of the condensing unit. Travels down here to the metering device. It flashes over. Now, remembering it takes a tremendous amount of heat to boil off this refrigerant in the coil, and if the coil is dirty, the filter is dirty, or there's airflow is restricted, it's not moving as much air across that coil and heat across that coil as it needs to boil this refrigerant off. So instead of this refrigerant being boiled off at this part of the coil, getting proper superheat, it just travels through the coil and picking up whatever heat it can, but not enough to change the state of the refrigerant, and travels back to the compressor and the inlet of the compressor with little to no superheat, just like our overcharged system. So again, it travels through this coil, not enough heat to boil it off completely, or at the proper point that it needs to boil off in the evaporator coil, and this returns back to the compressor in the saturated state or very close to the saturated state with low superheat. But here's where the difference comes in between a dirty evaporator coil and an overcharged system. So again, it goes through that compressor. It comes out as a hot gas and goes into the condensing unit. So this system is properly charged, metering device is feeding right, so this refrigerant runs through the condensing unit and it begins to get subcooled and it gets backed up right where it needs to be to have proper subcooling coming out of the condenser. So while pressures may be off, your subcooling is going to be exactly what it should be for a properly charged system coming out of this condensing unit. So that is always, that's why I always use subcooling to check the charge, because it doesn't matter if you have an overcharged system or a plugged coil or restricted airflow. If properly charged system is always going to give you the right subcooling. Even if this condensing coil is dirty, it's going to have higher pressures, but it's still going to have the proper amount of subcooling because the refrigerant is spending the proper amount of time in the condensing unit, in the condensing coil. Make sense? Everybody got it? Questions? Anything that I didn't cover here that you want to cover before we move on to the TXV? Is everybody staying awake? Okay. All right, let's move on here. Okay, good. All right, no questions. We're gonna move on. Okay, so that covers about 90% of what you're going to run into with a fixed metering device. It's going to either be undercharged, overcharged, or a dirty coil if there's a refrigeration issue. The other thing we'll want to touch on quickly is restricted liquid line dryer or kink in the line, which happens quite often in the liquid line. And the only way that you're going to know if you have restriction somewhere in this line is, and where that restriction is by a drop in temperature. So if you're measuring your pressures and temperatures and superheat and subcooling, and you've got good subcooling coming out of the condensing unit, and something's just not quite right with your superheat, and everything is, the charge is right, the coil is right, airflow is good, and it's a fixed metering device, what you're going to have to do is measure the temperature with your temperature probe at the outlet of the condenser, and then then measure it across the liquid line dryer, and then you're going to measure it as it enters the metering device. And if you have a drop in temperature of more than 2 or 3 degrees, you know that somewhere between that metering device and this the condenser coil is going to be, there's a restriction or there's a kink in the line. And a lot of times you can only see several feet of the line set here outdoors and several feet of the line set here indoors, and it gets to be a challenge if it's buried under a slab or running through an attic, and then you have to go on the hunt. Less often there's going to be a restriction or a kink in the suction line. And the one place I'll tell you is whenever it enters a building, especially when it goes up a wall and then makes a 90-degree turn into the wall, some lazy technicians will try and make that bend by hand and not put a 90 or do it with a bending tool, and that's usually where you're going to find that kink in that line. Okay. TXVs. I think we need to talk about the TXVs a little bit. Go back here and make this a TXV. Put our bulb right here. And we'll send the sensing bulb back for a TXV. Okay, so let's just do a quick review of a TXV and how they work. This is one of those mysterious refrigeration parts that takes a while to get your head wrapped around, but once you get it, you get it. So we'll start at the sensing bulb. Most of the time, the sensing bulb has refrigerant, the same refrigerant in it that the system has. So if it's an R22 system, it'll be R22 or R410A, the same. The sensing bulb is attached to the evaporator coil and the line right at the exit point or very near the exit point of the coil. Some manufacturers mount it externally, some will mount it internally. So you're going to have to look to see where it's at, but the sensing bulb is mounted at the outlet of the evaporator. Now, almost all, I shouldn't say almost all, 99% of the time, your system in the residential system is going to have an equalizer line. This is rarely a problem, but the purpose of the equalizer line is this. The sensing bulb is measuring at this point at the evaporator coil. The metering device is here. There is a pressure drop across this coil. So what the equalizer line does is it's attached to the outlet of the evaporator, and it comes back here to the TXV device, and it just equalizes the pressure so it negates the temperature drop across the coil. Very rarely is your equalizer line going to be any kind of an issue, but that's what it's for. It just takes the temperature. Okay, hold on just a second there. Just got a quick pop up there. I just got a quick question. Okay. Oh, yes, this is true. Robert goes, it is a problem when the Schrader valve isn't removed from the connection. Yes, this is true. But we're talking about a properly installed air conditioning system and properly operating air conditioning system. And I can tell you right now that about 95% of the problems with it, if you go on a call and that system was just installed, 95% of the time it's not the equipment, it is the installer or the installation process wasn't done right. Okay, so let's go back. I just have to tell you, Robert is now working in the HVAC field, so he's got great stories and a lot to add. Okay, so equalizer line comes off and is attached to the evaporator. Just balances the pressure between where the sensing bulb is attached and the TXV. So the TXV has one opening force and it has two closing forces. So let's talk about the opening force. The opening force is the sensing bulb on the TXV, which is attached to the evaporator, the outlet of the evaporator. Now, when this bulb is properly attached and insulated if need be, what happens when temperature of the outlet of the evaporator coil starts to increase? And if you think about it, when a temperature increases in a system, and this sensing bulb has refrigerant in there, as the temperature increases, the pressure in the sensing bulb is going to increase as well. So that sensing bulb runs through a little tube and is the opening pressure, and it pushes down on this diaphragm right here, and it pushes the valve right here open. So the liquid comes in at the temperature, and it's metering through this valve to the evaporator coil. If someone opens up a sliding glass door in the house and the indoor air temperature goes up and the outlet of the evaporator coil of course, is going to go up correspondingly. So does the pressure in the sensing bulb. The sensing bulb pushes down on the diaphragm and opens up this valve a little bit more to feed more refrigerant through to continue to maintain proper superheat and proper cooling in the home. So let's say that the sliding glass door is closed and the TXV is metering a lot of refrigerant through the system, but we've now lost a lot of that heat load. Well, the temperature on the outlet of the evaporator goes down. So the temperature goes down, the pressure goes down in the sensing bulb, and again, the sensing bulb is a closing or is an opening force, and that pressure starts to reducing the opening force on the diaphragm. Now, the opening force works together with the closing force on this TXV. Closing force is the evaporator pressure right here and the spring tension. So that holds this valve in the closed position. So these work back and forth together to open and close the valve. And when I say open and close, I'm talking it doesn't open all the way or close all the way. It just changes the metering of the refrigerant. So it opens to meter more refrigerant and closes to meter less. Rarely is it going to slam all the way shut or open all the way up. So once again, sensing bulb increases in temperature. It increases the opening force, and it pushes down against the evaporator pressure and the spring tension. Then as it starts to balance out and we go the opposite direction, the sensing bulb senses the temperature decreasing, pressure goes down, it relieves some of the opening force, and the spring tension with the evaporator pressure start to meter this or close the metering device just a bit. Now here's one of the things I'm going to warn you against. There's the spring tension adjustment. You can adjust superheat with a TXV. I don't recommend doing that ever because it takes 15 or 20 minutes for anything to equalize, and it's a quarter turn, and then you wait. And if you're not far enough, it's another quarter turn, and then you wait. And if you're too far, then it's an eighth of a turn back, and then you wait. And so I do not recommend doing any changes of the spring tension adjustment on a TXV valve in a residential system. They're set at the factory. If you're having an issue, it's not going to be an adjustment of the spring tension. Okay, questions? So far, is everybody hanging in there? Everybody still awake? Okay, let's take a look. Let's go back and take a look at what happens with an overcharged system that has a TXV. Okay, overcharged system with the TXV. If it is not grossly overcharged, this TXV is still going to be able to adjust the superheat. And even if it's undercharged, it's going to be able to open and close this valve enough to maintain the superheat over a fairly wide range of mischarged systems. So if it's undercharged and the temperature of the sensing bulb goes up, well, it's going to go up and it's going to push, and it's going to push down on that diaphragm until it's metering enough refrigerant to get the sensing bulb to the right and factory design temperature. And conversely, if it's overcharged, it's going to throttle back far enough so that it maintains a properly superheated evaporator coil. So it's going to maintain fairly constant, if not exact, superheat over a wide range of overcharge and undercharge systems. This is why you can't use superheat as an indicator of an overcharge or undercharge system when you have a TXV. So wide range of charging, undercharge or overcharge, superheat is going to remain the factory setting, but when you go over here and do the subcooling, you're going to have high or low subcooling depending on whether it's overcharged or undercharged system. So what can go wrong with the TXV? First thing you need to check before you do anything with the TXV is, first of all, make sure that the system is, you don't have any restricted airflow, because remember, even with restricted airflow and a TXV, it's gonna maintain superheat to the factory setting. So that's not a very good indicator if you suspect a TXV problem. Superheat is not a very good indicator there. So before you start doing anything, you need to check your charge at the condensing unit. You need to check to make sure that you have proper airflow and that the coil is clean. You also need to make sure that the sensing bulb has not fallen off of the evaporator coil. And I'm going to tell you, I go to more air conditioning calls in my life that technicians use zip ties to put the sensing bulb on. There are copper straps to strap the sensing bulb to the evaporator line. That's not what zip ties are made for. You also need to make sure that if it's not a Lennox system, that this sensing bulb is insulated. If you're still seeing problems, suspect a bad TXV. After you check those, then it's time to go hunting down. Usually what happens is the sensing bulb loses its charge. So what will happen is there's no opening force. Now this is designed, it's still going to meter refrigerant through here. It doesn't close all the way. But you're going to end up with ice coming out of the, right at the end of the outlet of the TXV. So sensing bulb is usually the issue. If you really want to check it, you can unmount the sensing bulb and you can put it into, go get a glass of hot water and put it in a container and dunk that sensing bulb into the hot water. So what happens, we lost our sensing bulb. So you now have your sensing bulb removed from the outlet of the evaporator, and now it's in your glass of hot water. And it raises the temperature of the sensing bulb, which raises the pressure of that sensing bulb. So what should you see happen as this pressure increases on the TXV from the sensing bulb is you should see an increase of pressure on the outlet to the evaporator. So if you dunk this in hot water and you're still down at 30 degrees on your saturation temperature and it's not raising up, you know you have a bad TXV. So that's your warm and fuzzy. If you suspect a bad TXV, dunk it in the hot water. Make sure that the sensing bulb was pulled out and the cover to the evaporator compartment is closed, and run that system, and you should see that corresponding increase in pressure and changing of pressures on the suction side as that TXV opens and closes. Okay. Let's see, Robert. Sorry, just missed you there. Yes, Robert, yes. Robert's in Texas, so a lot of the the air handling units for the air conditioning or heat pump units are in the attic, and I'm sure he's not liking that too much these days. And yes, I'm glad you brought that up, Robert. Let's go back. The other thing, and I can't remember the exact statistics here, but a lot of, I don't know what percentage of it is, but it's not a majority, but it's more than a few. TXVs are replaced because the inlet is plugged with debris. Some of the TXVs, depending, will have a little screen right in front of it where the liquid line comes in to catch the bigger debris. But if you don't use nitrogen when you're brazing, that creates carbon, and that carbon gets caught in the TXV and plugs up your either the screen, and if it doesn't have a screen, it can plug up your the metering part, that little valve right there. All right. Okay, so any questions for me on what we covered tonight? Anything that I didn't cover that we need to? Okay, so everybody go up to their mood. Everybody go up to their mood there, and then clear your mood, and then give me a thumbs up or a thumbs down. Okay. All right. So if you're already through Module 3, and hopefully this reinforced what you've already learned. If you're just entering Module 3, make sure you go back and look at the service calls. Those are some real life situations with pictures, temperatures, and pressures for you to think your way through. And please post on the forums and get involved there as we go through. As you get through Module 3, this is one of the most important modules. Do not rush. Make sure you understand it. And I know some of you have come back and done a few more brushing up on Module 3. I would encourage you to do so as you go through this the course. So if you don't have any questions, last chance. We're going to call it a night, and pay attention to the calendar in our HVAC group. I'll post our next online class up there, and I need some input from you all so that I can guide this class to where you need it to be, and not what I think you need to know, and what you need help with. All right, so I'd like to thank you all very much. One last chance for questions, and if not, I will talk to you next time. Thanks, guys.